Next equation in Chapter 6 you've got to be familiar with is the de Broglie wavelength. So de Broglie showed that matter, that particles have a wave nature to them. That's why this is important, and how you tell that you're calculating a de Broglie wavelength and not a wavelength for light is there's a mass term. The mass has to be in kilograms. In order for this equation to work and for you to get the correct answer, you have to be in the proper units. The mass has to be in kilograms. Planck's constant, all of this is breaking apart what a joule is. So a joule second. What I've circled there is another representation of a joule, a kilogram meter squared per second squared. So to get kilograms to cancel, your mass must be in kilograms, and your speed, the velocity of the particle, has to be in meters per second to get meters per second to cancel. So here is a typical de Broglie wavelength problem. What is the de Broglie wavelength in nanometers associated with a 2.5 gram table tennis ball traveling at 15.6 meters per second? So recall the formula. The de Broglie wavelength is Planck's constant over the mass times the velocity. The velocity, not wavelength or frequency. Speed. So this type of problem is a plug and chug, but write all the values. Planck's constant 6.626 times 10 to the minus 34 kilograms meter squared, second squared, times second. The mass is given to us in grams, but it must be kilograms. So 0.0025 kilograms. The velocity needs to be meters per second, which it is. Plug in those values. Kilograms cancel. Seconds cancel as well. This is meters squared. One of those meters cancel. You're left in units of meters. If I do that math, reframed everything, 1.698. You should use 2 sig figs, but times 10 to the minus 32 meters. But the question is asking for nanometers. 1 nanometer is 10 to the minus 9 meters. So 1 point, round to 2 sig figs, 7 times 10 to the negative 23 nanometers. Extremely small number. meaning that that's why that you do not see a table tennis ball, a ping pong ball. You don't see its wavelength when you're playing ping pong or table tennis because it is so small. For a small particle, subatomic particle, this is something that is significant. Quantum numbers. Another part of Chapter 6. It's not calculations, it's rules. So, before going into how you would do a problem like this, you have to know the rules. N is the principal quantum number, and it can be values 1, 2, 3, ... all the way up to infinity. Practically speaking, infinity means that the electron has been ejected from the particle. L is the angular momentum quantum number, and that has values of 0, ... all the way up to n minus 1. So, in other words, L cannot equal n. What L tells you is it tells you the shape of the orbital of the electron, or the electron orbital. You'll see those shapes in your classes. This is just summarizing the quantum numbers. M sub L. Each of these numbers are dependent upon the previous one. It can be a range of minus L to plus L. It's the magnetic quantum number. It tells you the orientation of the orbital described by L. Then last, M sub S can be plus 1/2 or minus 1/2. That's the spin quantum number. It tells you whether or not, whenever you get into diagrams, electron or orbital diagrams, a plus 1/2 is indicated by having a spin of up. Minus 1/2 will have an electron being spin down. When you learn about the Pauling exclusion principle, it means that every electron has to have a unique set of quantum numbers. This will make a little more sense, but plus, spin up, minus, spin down. So to the question at hand. So if you have n equals 4, and that's all you know. They said, what are the names of the subshells or sublevels? And then n equals 4 shell level. If you know n, you know the level. If you know n and L, you know the sub-level or the sub-shell. But for this problem, all you know is n. Therefore, L can be 0, 1, 2, or 3. It can be any of those 4 numbers. We don't know anything about this particular electron other than n is equal to 4. So those subshells, 0 means that those electrons can be in an s orbital. 1 is a p orbital. 2 is a d orbital. 3 is an f orbital. All we can say, if we only know n is equal to 4, is that you can have an electron in any of these subshells. It's all the information that we know. Earlier in the play posit, you were given the rules, or recall from your lectures, what the rules for your quantum numbers are. So here we've got what are the 4 quantum numbers for an electron in a 3p orbital. 3, when you see this kind of notation, that tells you N. The letter, that tells you L. So we know those two numbers for a fact for this electron. So we know that N is 3, L, so 0 is an s orbital, 1 is a p orbital. So L is equal to 1. So those two numbers we know. M sub L, we don't know. We're not given that number, but we do know it could be -1, 0, or +1. Refer back to the rules from earlier in the play posit. So that means that you've got an electron in the n equals 3 shell. Okay, so the third period on the periodic table, or the first row transition metals. But L here is a 1 that tells you that it's in the p block, the right side of the periodic table. And then each of these orbitals can hold 2 electrons. +1/2, or -1/2, +1/2, -1/2, +1/2, or -1/2. Could the spin of the electron could be up or down for each of these orbitals. So the question, what are the 4 quantum numbers for an electron in a 3p orbital? The 4 orbitals, the 4 quantum numbers, excuse me, are here. N and L we know for sure. M sub L we can narrow it down to 3 numbers, and then for each orbital we can say that the electron is either spin up or spin down. That's what we can deduce with this information that's given.